Modern cyber-physical systems, like autonomous vehicles, are dense webs of interacting elements. Mechanical drivetrains, software control loops, and electrical data streams execute simultaneously. To prevent catastrophic failures in these complex networks, engineers rely on the AIAG VVA failure mode and effects analysis framework. This is a standardized methodology primarily documented and managed in massive spreadsheets. This creates a conflict in the engineering process. The system being built is a dynamic, highly coupled network, but the tool used to analyze its safety is a static, fractured document. Because the spreadsheet cannot execute logic, human engineers must manually map potential failure pathways line by line. They attempt to mentally trace how a single broken sensor might cascade across thousands of rows of data. This mental modeling often fails to account for sneak circuits, hidden cross-connected pathways, where an electrical fault triggers a software error that compromises a mechanical break. These gaps lead to inconsistent data, delayed product cycles, and unrecognized vulnerabilities. SysML v2 addresses these limitations by utilizing a rebuilt kernel metamodel, or KerML. This provides a rigorous technical language designed for computational logic rather than human estimation. SysML v2 integrates FMEA directly into the design logic, allowing it to function as an executable extension of the system architecture. Achieving reliability in modern engineering requires moving past retroactive human inference and adopting algorithmic precision. Previous modeling languages struggled with ambiguous hierarchies that made safety analysis difficult to automate. SysML v2 resolves this by enforcing a strict usage-centric modeling philosophy. It distinctly separates the abstract definition of a component, using the def keyword, from how that component is specifically applied in a system context, known as its usage. This structural layout shows how the textual syntax translates directly to the structural analysis phase of the FMEA framework. On the left is the SysML text code. On the right, the system parses that code into a node graph, branching a top-level vehicle node into a specific brake caliper structure node. The code uses the part keyword to establish the physical architecture, while the perform action command ties an intended function directly to that physical component. By directly binding behavior to physical parts, the model completes the functional analysis phase of the FMEA process without any secondary data entry. To measure that function, engineers write a requirement def component. This embeds a strict mathematical constraint, like a maximum stopping distance of 30 meters, directly into the functional network. These embedded constraints act as technical thresholds. If a component breaches this mathematical rule during analysis, the system registers a failure. Because the model structure mirrors the FMEA ontology, the first three columns of the traditional safety spreadsheet, structure, function, and characteristics, are extracted from the syntax tree via standard APIs. Mapping the system architecture exactly to the safety ontology prevents version control conflicts between the design and safety teams. With the baseline established, the process moves to steps 4 and 5, failure and risk analysis. Here, a failure is defined as a deviation from the constraints we just set. To test these deviations, SysML v2 integrates with the Risk Analysis and Assessment Modeling Language, or RAML. Under the RAML standard, failures are treated as executable anomalous states, defined in the code as a state def, rather than passive text descriptions. This visual pathway demonstrates direct fault injection. The system forces the brake caliper's internal state variable to switch from a nominal state to a failed state, dropping its friction coefficient to 0. This forced deviation does not remain isolated. The anomaly propagates physically through the architectural connections and data ports, traveling along the brake pressure line into the overarching vehicle speed output. The cascading failure eventually hits the top-level system requirement. The mathematical formula evaluating stopping distance registers the anomaly, flipping its Boolean output from a green true to a red false. Back-end simulation engines parse this exact code block to run Monte Carlo simulations and traverse the graph logic. By tracing data pathways algorithmically, the system can discover cross-connected failures that an engineer looking at a static spreadsheet could easily miss. Simulating these failures allows the system to identify the consequences of cross-connected dependencies based on the structure of the model. Identifying the risk leads directly to FMEA Step 6, optimization, where engineers must design mitigations for the identified vulnerabilities. Risk is quantified using 3 specific parameters: severity of the failure, its probability of occurrence, and the likelihood of detection. In SysML v2, these parameters are bound to the hardware reliability metrics and sensor logic written into the model, providing a data-driven basis for risk scores. To mitigate the breaking risk, an engineer might propose a design optimization. This flowchart shows a single serial connection line breaking and reforming into a parallel AND gate structure to insert a new redundant software controller. By writing the new part definition into the code, the physical data flow of the architecture is updated. The exact moment this new code change is committed to the system, the API backend immediately scans the new dependency network. It recalculates the system's underlying fault tree logic, shifting it from a single point of failure to a redundant parallel structure. Because of this structural change, the mathematical probability of occurrence drops. If a diagnostic sensor was also added to the model, the detection score improves, driving the final risk priority number down to a threshold. Every related FMEA view, table, and dashboard connected to the model updates based on this single parameter change. Autotracing keeps the safety analysis synchronized with the design, reflecting engineering changes in the risk profile as they are committed. The final phase of the framework is Step 7, documentation and reporting. For a model to provide enterprise value, it must be part of a continuous digital threat. Disconnected modeling tools still result in fragmented data. SysML v2 establishes a single source of truth, utilizing standard REST and OSLC APIs to link requirements, simulations, and architecture into a single repository. Compliance reports function as dynamic, on-demand queries that snapshot the current architectural state captured in the model repository. This synchronized reporting reduces documentation overhead and prevents the late-stage recall costs that happen when design and safety teams operate in disconnected silos. Hardware engineers, software developers, and safety specialists collaborate through a transparent, shared view of the system's technical risk profile. These structured, executable datasets lay the groundwork for the next evolution of engineering, where machine learning algorithms can analyze the graph to help predict vulnerabilities before they are even built. Using SysML version 2 for model-based FMEA provides the technical framework required to verify safety in systems with high levels of cross-domain integration.